Here we go. This is video 5 now. I don't know. We're starting off talking about angular quantities. So we are getting close to the end here. A couple more pages left. But at this point in time, we're going to be basically translating almost everything we've talked about into what it means to work around an angle. So to start things off, we're going to talk about radians. And hopefully you've talked about this in honors geotrig or math analysis, but radians are another way of measuring angles just like degrees. If we were to label this coordinate system with degrees, we'd start at 0 degrees here. This would be 90. We're at 180 over here. 270. And then we're back to 360. Radians are just another way to kind of label this, and they'll give us some advantages around some of these other areas as we go. Basically, because it's based on the circumference of a circle, and that'll allow us to get some quantities a little bit easier. But starting things off here, starting at the positive x-axis over here, we start at 0, just like degrees. Up here, pi half is up there. This is pi. We have 3 pi over 2 down here, and then over here that's 2 pi. This is basically how much circumference we would have traveled, given that this would be a 1 unit length circle as far as the radius goes. Convert between different systems of measuring angles and rotation and things. It's not too difficult. Essentially, we get this part here, that 2 pi radians is the same thing as 360 degrees, and that is also the same thing as 1 revolution. So you can use any of those things to convert from one way of measuring an angle to another. So let's look at a first conversion then. So to convert radians to degrees or vice versa, set up a conversion factor. So if we have 45 degrees, we put in our fraction bar. We want to cancel the degrees out, so we'll put it on the bottom. And then we'll put 2 pi on top for radians. And if we multiply that out, we get 90 pi over 360, which will give us pi over 4th radians. This also works the same thing, so for revolutions, so to convert radians to revolutions. We just take 2.5 revolutions and multiply by 2 pi rads over 1 revolution. Revolutions cancel, and we wind up with 5 pi radians. So converting between these things is fairly simple. Now, other things that are going to be useful for us, if we were talking about an object traveling around this circle, knowing how much distance it traveled would be helpful. So to find the linear distance of a curve, if we know the sector of an angle or the sector of a circle or how much angle it traveled through, we can use a really simple formula. That formula, we'll get the letters and stuff here in a second, but in the formula we have arc length, that is S. This will be the linear distance that the thing actually traveled, where R again is the radius of the sector or circle that we're looking at, and this is going to be theta, that's the angle or of the sector that has moved through. This must be in radians, that's why we're actually talking about radians, otherwise it won't give you that circumference that we're looking at. So this equation is very simple, it's just S equals R theta. And if we travel around the full circle, we would have 2 pi in radians, and 2 pi times the radius would give us the circumference of that circle, which makes perfect sense. All right, so let's continue on to page 6. So distance is kind of like the angular. The arc length is kind of like the angular version of distance. We're going to kind of go through here and get the angular versions of different variables we talked about throughout the year. So angular speed or velocity. The definition of this is how many radians are swept out in a given amount of time. If an object is traveling along the arc length in a given amount of time, we can calculate its angular speed basically just by using this little formula. We have delta theta divided by delta time. And because this is a slightly, we can't use v for this because, once again, the thing's not going straight. We have to come up with a different letter. So when we do this, we are going to use something called an omega. Omega is a Greek letter. It looks like curvy W. I've heard people call it butt cheeks before too. But that works as well. So omega is the angular speed or velocity in radians per second. It's pronounced omega. Delta theta is how many radians are swept out, or the change in angular position. And once again, delta t is the amount of time. If a solid object is spinning like a DVD, then every point on that object has the same angular speed. However, all points are potentially sweeping out a larger arc length, depending on how far away the radius is, but the angular speed, how fast they're changing their angle, will be the same. So this is going to be radius independent. The SI unit for omega is radians per second. However, there are other popular units such as revolutions per minute, or RPM as far as engines are concerned, or revolutions per second. And just like before, when we looked at the other conversion factors for things, we can convert just the same. So if we were going to try to convert revolutions per minute into radians per second, it works the same way as any other conversion does. So we know that as far as revolutions go, we have 1 revolution for every 2 pi radians. So revolutions cancel. We're in the right unit now, to the top anyway. And we have to cancel the time unit still, so we have 1 minute over 60 seconds. Cancel, cancel. And in this case here, we wind up with 240.7 radians per second. We can also connect angular speed to linear speed by using this equation, where v equals r omega. And if you notice here, so far the rule for how to transfer from a angular measurement to a linear measurement is just take the angular measurement and multiply by the radius. That's the translation piece. Note linear velocity does not depend on the radius of the object or the distance the object is from the center, whereas omega does not. So if you were to sit on a merry-go-round, if you were in the center versus the outer edge of the merry-go-round, you will be traveling faster on the outer edge in a linear capacity, and slower in the center in a linear capacity, but your angular speeds will remain constant because you're moving the same amount of radians per second. Our next variable is called angular acceleration. You can notice we're kind of moving through kinematics at this point in time. So angular acceleration is how fast angular speed changes in a given amount of time. If an object is traveling along the arc length while increasing or decreasing its angular speed, we can calculate its angular acceleration. And just like before, when we looked at linear velocity, linear velocity's equation was this, where we had essentially delta x over delta t, and acceleration's linear form was just delta v over delta t. To follow suit, since angular velocity is kind of like our linear velocity, we're just going to basically do the same equation, but just translate it into angles. So our equation will be the change of omega, the change of angular velocity, divided by delta t. And the letter we use to denote angular acceleration will be this guy. Looks like a fish. This is called an alpha. This is the Greek letter for a, which would make sense. So a is angular acceleration, once again measured in radians per second squared, where radians is basically just replacing meters in our normal linear forms of these things. If a solid object is spinning like a wheel, then every point on that object has the same angular speed. Therefore, every point would exhibit the same angular acceleration. So once again, we're seeing that because of the way things are spinning, these kinds of things, angular acceleration, angular velocity, they are independent of radius. But depending on where you're sitting, your linear acceleration will be much different. All right, let's progress onwards. And we can connect angular acceleration to linear acceleration in the same way we have been doing. Essentially, we take our angular form of our variable, multiply by the radius, and we're back into linear. So linear acceleration, which is kind of like the tangential acceleration, that will just be r alpha. Note, your linear acceleration does depend on the radius of the object or distance the object is from the center, whereas alpha does not. Radial or centripetal acceleration, and this is referencing the book, so I don't know if you have access to that, but they give a different equation for determining the centripetal acceleration at this point. Because before, when we talked about acceleration in the centripetal stuff, we talked about v squared over r. But because of the way, because of the equations we have, v is just r omega. And if we keep that squared there, we can get this, r squared omega squared over r, and the r cancels with the square, giving us r omega squared. So that is an alternate equation that you can use to determine what the radial acceleration is if you need to. Okay. Moving on from kinematics, we're going to skip projectiles because they don't really do much with rotation. We go into Newton's laws. And just like before, we had an angular version of kinematic variables like speed and displacement and acceleration. We have an angular version of force, and that is called torque. We're going to pick up in the next video, so scroll down and we'll learn more about torque in just a moment.